And we have also the possibility of impulse. Well, impulse is sort of like plucking, but often you don't have as much control over it. And sometimes you resort to extremes. Get more bang for the buck out of TNT. And so here's an example of that. And this is just to contrast to what we heard about earlier, where we could trace a 2-mile wavelength. Not quite that long, but this is a military mortar, a 4-inch, which is a fairly large mortar. And the mortar is a low angle trajectory artillery. And the explosive comes in wafers that are the size of the chamber, and you slide them down, and your number of wafers depending on how far you want the projectile to go and so forth. And so we loaded the barrel with wafers, put in a plastic sleeve, filled the plastic sleeve with water. And when we set off the explosive, you get a great kick in the horizontal direction, an impulse in the horizontal direction. Of course, there's a vertical component also, but it turns out the horizontal travels farther. And this is all there is water vapor. And we traced SH wave refraction for 2 miles. Now, it wasn't a 2-mile wavelength, but we were able to trace refraction and using the SH component. So I've shown you sort of the old man's version of plucking and steady state, and I hope that we can kind of agree that it's mainly a matter of scale. Thank you.
Sir, how many real mortars have you fired?
I'm sorry, how many what?
Real mortars.
Real mortars that I fired.
Yeah, maybe a Pendleton or something like that.
One.
One.
Several times, but it was the same mortar.
Okay.
Now, the Swiss have started to explore that same concept, and they built just a vertical column with explosive chamber at the bottom and filled it with water. They could make the chamber longer or shorter depending on how long they wanted the pulse. And they have tested a bridge that way, but apparently it was not particularly either cost-effective or technically effective way, and they did it only once.
Okay, well, amongst changing, thank you, Professor Woods, for discussing that. You have been a pioneer in dynamic testing for many years.
You just like him because he's a sharpshooter. Yeah, he's a great sharpshooter, so be careful.
That is true as well, I'm sure. Now we're going to turn the time over to Nat to explain the basis for really why we're here, why we ended up having a workshop here, which we really appreciate. So,
yes. Yeah, and we do want to thank you very much, because this is wonderful for all of us.
Well, really our pleasure, and you know, we have been working now for 4 days, and it's really, I told the guys, you know, this is really making me think I should resign as the department chair. This is far nicer to do. So it's really been a wonderful experience to work with a team from University of Texas at Austin. And what I will do is I will speak a little bit about the project itself. As you can see, we have here a number of names. Basically, we were preparing this presentation this past night. And so we did not know exactly how we were going to put together. So what I'm going to do is I'm going to provide an overview of the project. But then we will also go a little bit and try to present some limited records, some limited results from the field itself. So after I'm done, we will hear a little bit from Brady, who's going to speak a little bit about surface wave testing and ambient vibration measurements. Anu Meng, he's going to speak a little bit about what was captured with some of the sensors. And finally, because we had two groups of sensors, one were geophones, the other one were accelerometers, we will also hear from the team from Rutgers. So John DeVittis is going to speak a little bit about some of those results. These are most preliminary results. And as I said, they were developed 2 o'clock in the night. So 4 things I will just provide a very brief overview of the project, what were the objectives, so what is the goal, and what is general scope of activities. My understanding is that based on the applications, that these are more structural engineers than geotechnical. So what I will do is, in a way, to help you a little bit better understand what kind of numerical modeling we are doing, I will just very briefly introduce some basic concepts from soil dynamics or foundation dynamics, and also say a few words based on what are general effects from dynamic soil structure interaction. So what are we expecting to see in our bridge? Very briefly, I will say also about another activity which is going in parallel, and that is related to numerical simulation of these bridge soil systems. But the most of the presentation will be related to field implementation, because that is why this workshop was organized. Okay, so this is the name of the project. So informing infrastructure decisions through large amplitude force vibration testing. So a little bit about motivation for this research. So you are all very well aware that we are dealing with aging infrastructure, and as such, we would certainly like to have some kind of tools where we can make some kind of safety assessments. How we typically assess those structures, there is the whole field of structural identification, and my colleague Frank Moon, he will speak about it. That is his area. So where we can say is that yes, there were huge advances in the past few decades in terms of what kind of sensing technologies we have introduced, what kind of simulation models we have, and all kinds of procedures or algorithms we have developed to do calibration of those models. But this is where Professor Wood's talk perfectly fits. What is the problem? The problem is what kind of input we have in our testing. What we can generally say is that if we speak about static loading, I think there was pull release, impact, so shakers. These are all still relatively low-level inputs, which can provide us information only maybe similar to operational limit states. So we do not get information which would give us at least some hints what we can expect regarding the performance of structures once we get to extreme events. And that is what we would like to do by introducing these high intensity loads using mobile shakers. So this could also be illustrated this way. So what we can say is that conventional structural identification is in this zone, where we can say is we also have these low-level mechanisms like unintended composite actions, non-structural components, frozen movement systems. Like for our bridge, it could be. This doesn't show. Yeah. Oh, this one is better. So if you would like to overcome those, you have to go with a higher load, and that is why we are saying is that is where we need. Where is it?
It's a little push right at the, right at that end. There's a little knob sticking up right in that dark color.
So that's why we need shakers to go beyond this level. and that we can say is that we can approach safety limit. And as you're going to see, this is what we are trying to see, and there will be a very brief discussion. Are we starting to see any non-linearities by applying loading from shakers? Okay, so very directly about the goal of the project. This is what is our overarching goal, is so to explore and hopefully establish the ability of these shakers to be used in performance evaluation of structures and prediction of future performance. But there is one distinction, is that unlike how we are currently evaluating bridges, we would like also to bring into consideration of dynamic soil structure interaction. So in terms of what are more focused objectives, I will try to speed up a little bit this introduction. So first of all, what we would like to develop, we would like to develop force vibration testing strategies. And as you are going to see, to develop those strategies, we are doing numerical simulations and conducting all kinds of parametric studies to find out how we can identify parameters of the highest interest. Something what again falls into domain of my colleagues, John Rubitis and Frank Kuhn. So how to develop data interpretation frameworks. So if we go on a bridge, so how we can interpret those data to get an understanding about performance of structures. And finally, what we identified in the proposal, this is why we are here today, is that once we develop these strategies for testing and also strategies for data analysis, can we validate those by deploying our mobile shakers on a bridge and analyzing those data? Okay, so probably we can skip all of those. So as you're going to see later as we start describing our validation testing, is when we were thinking about what we would like to do is, yes, this would be ideal, that we deploy this high intensity shaking on the bridge structure and to evaluate the response, not just of the structure, but also of the ground. And we hope that we will be able to infer from measurement of those vibrations of the ground the significance of dynamic soil structure interaction. We did not have this luxury in the field. You are going to see that we had very constrained conditions in the median. So we are really going to measure only vibrations along the median, so only in one direction. Okay, for those who are not that much familiar about foundation dynamics and some basic facts about the effects of dynamic soil structure interaction. So what are we trying to do is, when we speak about the dynamic soil structure interaction, we primarily want to encompass into evaluation of the dynamic response, what we can say is loss of energy through wave propagation, so which is not being considered. Structural models are mostly assuming that you have a fixed pace. And if we think about what are the effects of soil and the effects of soil structure interaction, something what is probably a little bit more familiar is that soil is, if we are talking about earthquake loading, it is going to lead to amplification of motion. But when we speak about the effect of soil on dynamic soil structure interaction, first of all, soil flexibility is going to change the flexibility of the overall system, and the fundamental frequency of that joint system is going to go down. What is going to be a very important effect, and you are going to see some results even from, I guess they are mid-60s, in Professor Wood's book, that this radiation of energy through wave propagation, it is going to cause a major increase in the overall, you may say, equivalent damping ratio of the soil structure system. When interaction is having stronger effects, it is when the structure is more rigid and soil is softer, and vice versa. So if you would have a flexible structure on a relatively rigid soil, interaction effects would be weak. Something what various studies have shown that in general, that if you would take into consideration effects of dynamic soil structure interaction, you may say is that your design would be a little bit more economical. So by ignoring it, we are usually having more conservative designs. Now, what is important for the modeling, which I will just very brief numerical modeling, which I will briefly describe. Yes, we can always do modeling of these soil structure interaction problems using direct approach, which means we model everything together. And that is going to quadruple or even more the computational power you will need to analyze such structures. The other approach which we can use is substructure approach, where we can say this is pretty much describing the problem for earthquake loading analysis. But in general, what we are trying to do is we are trying to separately describe the soil system and separately the structure. So what we are going to do is we are going to analyze the soil system to develop something what we describe as impedance functions. And then those impedance functions are going to be attached to the base of the structure. So what are those impedance functions? These are different solutions which were developed from maybe analytical solutions, maybe numerical solutions for any possible situations. Any shape of a foundation, surface embedded on a layered system, embedded in a layered system. So various kinds of solutions, but in most cases we can describe those in very simple form as described here by this expression. So as an example, vertical impedance, we typically describe impedance by static component and multiplied by these two coefficients, where you can see the damping constant C is multiplied by this A0, which means frequency. Okay, this is proportional to frequency. So what is important to see about this, that impedances are functions of frequency. So these are not constants. So these are functions of frequency. And they are going to depend on many elements. They will depend on soil properties. So primarily shear modulus, damping, and Poisson's ratio. They will depend on shape of the foundation, depth of the embedment, presence of a rigid base. And we are thinking that on our site, Hobson Avenue Bridge, where we will go tomorrow, that we might have this situation, that we might be testing on a stratum. It will depend on mode of vibration, dynamics and frequency of loading, and foundation flexibility. So just very briefly to show some. So there are these various modes, translational modes and rotational modes. So you will see that we will be primarily interested on our bridge in this vertical and swaying mode on the bridge. So just simple examples. Let's say this is for circular foundation on a half space. Static stiffnesses will look like this. So we have modulus of soil, shear modulus of soil, and radius, and Poisson's ratio as components. While those coefficients, that stiffness and damping coefficients, they are what we said, a function of frequency. And as you can see, they can vary significantly. Okay, going to the research from 60s and Professor Wood's book. So here you can, for example, see, for those who are from structures, you know that you are typically dealing with damping ratios, what, 2-3%? Okay. If you look at what would be the damping ratio for a foundation or any kind of rigid structure on soil, these are so-called mass ratio, and if that structure is light, so we are on this end, we might get damping ratios, for example, for vertical motion on the order of 40%. Okay. And as you can see, that translational modes are more damped than rotational modes. So you can see that rocking is providing lower damping. Okay, I think for the sake of time, I'm going to skip some of those. This might be of interest for what we are currently doing on our bridge. I said is that we might have below us stratum based on some measurements. And if that is the case, so what happens is that every stratum has its own natural frequency. And if you excite at that frequency, what you are going to get for the foundation, very low damping. And as you can see here, is that for low frequencies, which are typical, let's say, where you might say, see fundamental frequency of the stratum, that you have very low damping. And the reason is there is very little surface wave propagation, and body waves, as they propagate, they cannot propagate. They will be simply reflected. So you are not propagating energy. Okay, we can probably skip some of those. So these impedances we have implemented into our numerical models to conduct a parametric study to evaluate. So what is important for the response of this bridge soil system? We are not going to speak much about the results, but we can show at least what we are doing is, so first we started at the very beginning with this 2D model of a hypothetical model. We probably spent almost 9 months identifying the bridge and getting permission to do the testing. So we did not know what was going to be the bridge, so we were conducting the study on a hypothetical bridge structure. And the first analysis was done on 2D models, so Sharif Farag, he was doing the study, and as you can see, the variables which we concentrated was what is the soil velocity. So we varied it between 2 and 400. We changed, for example, we assumed that we are talking about here circular footings under piers, and we varied also column height. So this ratio between column height and, or we can say the height of a building and the width of the building, we typically call slenderness ratio. And what is important about this slenderness ratio, if you have higher slenderness ratio, then this rocking motion of a building becomes more significant. Okay. So here you can see, for example, what would happen with a typical 2D model of such a system. So what we would do is like similar to what we do on actual bridges, we would do frequency sweeps. So analyze a response at a harmonic frequency and for a range of frequencies. And you can, for example, see for one particular frequency. So this would be, for example, for this point on the deck. So harmonic loading, and we can see harmonic response. Clearly that for the vertical motion of this point, it seems like there is superposition of two motions. One might be maybe as a result of tilting, another one of maybe footing moving up and down. So similarly, what we could evaluate from there is what is happening with the foundation. And you can see that as we have this horizontal excitation, we are at the same time observing horizontal sliding of the foundation, and we are also observing rotation, rocking of the footing at the same frequency. The data were looked in time domain, but also in frequency domain. So if this was our loading spectrum, where we can say is for a range of frequencies of interest, for example, here from 0.5 to 4 Hertz, so where we had like unit loading, looking into various scenarios, what kind of responses we are going to get at any point on the structure or the foundation. So how the spectra look like, and not just displacement spectra, but what is probably going to be of higher interest to us as we compare with our field data, how velocity spectra and how acceleration spectra compare. Okay, so similar you can see for the rotation. So there is this general fundamental frequency of this soil structure system. So if you compare this frequency, it would be the same as for the superstructure. So we are looking into how we can present those data, and as you can see, for example, if we would increase pier height, which means increase the slenderness ratio, we would see a decrease in the fundamental frequency of the overall of the whole structure in this swaying motion. Skip. So what is going to be the task? The task will be to look into effects of all of these parameters and see. So here is, for example, the effect of slenderness ratio and the effect of ground conditions and, let's say, geometry of the foundation. So in this case, radius of the foundation on the fundamental frequency of the structure. There is no question that there are effects. We got design drawings for this bridge we are testing about 2 weeks ago. So this is the model of the bridge. So 3D model of the bridge. And so here you can see it is approximately 216 feet long, about 40 feet wide. So it has 2 spans. And these dimensions are perfectly matching every element in the drawings. So foundation, pier cap, piers, girders, and so on. And here you can see. So how, for example, if we went with the assumption that we have a rigid base, this is what would be the fundamental swaying mode of this bridge. It would be good to hear once we get results from the bridge deck, whether bridge deck is really doing something like this. Is that realistic?
I think it is. I felt it the other day. Standing mid stairs at the end.
Everybody can judge tomorrow on the shape. You'll know.
Okay. So maybe one number to remember, 4.7 Hertz was numerical model. So, but the same model was analyzed by including also impedance functions. So as you can see on the foundation, we were thinking of what should be the best model. Yes, the best model would be we would have a large numerical model of the soil with embedded foundation, and we evaluated impedances that way. But if we used existing solutions, should we use a single or multiple? Considering the length of the foundation, we felt that it would be better that we, let's say, support with separate impedances below each of the piers. So there are 3 sets of springs, so it doesn't mean just these. There are also rotational springs which are not plotted here. So those which prevent rocking. And what you can see now is that we are starting to see real rocking of this foundation. And as a result, unfortunately this number is too small. If you remember, for rigid foundation it was 4.75, this one is about 4.65. So we got a decrease in the fundamental frequency of about 0.1 hertz. But this is for the assumed soil conditions. And I think what we use, 200 meters per second, which is higher than what is the actual velocity. Okay, so let's go to the most interesting part, and that is related to the deployment of University of Texas mobile shakers, in particular T-Rex. Okay, so what are the objectives of our work? Well, the primary objective is to measure all the response of all components. And when we say all components, we mean components on the superstructure, substructure. Unfortunately, we could not dig down to the foundation, but we have placed so many sensors close to the foundation so that we can say it's almost foundation and the ground in vicinity of the structure. We would also like to assess transmissibility. So what is the transfer of motion from between different components of this soil structure system? And something what we would also like to see is, can we use mobile shakers to at least estimate what are foundation impedances? Probably the chances will be the highest for vertical impedance because the mobile shaker was placed directly above the foundation. So the loading is through the piers. So for vertical impedance, we can say, yes, we might be the closest. But maybe we can think about our own inversion procedures, how to get some feel for what are other impedances. So once we conduct our measurements, we will compare against the models. And if you remember, that's similar to what was done already in structural identification, is we would also like to see whether we can do some model calibrations, which might help us in the future to work on problems where we have no information. And finally, we can say, and I believe that Frank is going to address a little bit. There is another smaller system called Thumper, which was developed as a part of Anders' project while Frank was still at Drexel University, but he and his team are now working with it here at Drexel. So we will see measurements were done also by Thumper, so we will see how they compare to what we can get from T-Rex. Okay, a little bit about the bridge. So the bridge is approximately 30 miles south of here in Hamilton Township. So it is crossing Interstate I-195, which is going east-west across New Jersey. We can say east of Trenton. So it is a two-span bridge, so continuous, span steel girders or concrete bridge deck on steel girders. It is about 40 feet wide, so you can see, so 40 feet. We have a sidewalk of about 6 feet on the western side. So just a little bit look into superstructure. So steel girders, 5 steel girders, continuous girders, supporting concrete bridge deck. And the first part of the testing was on Monday when we, first of all, deployed all of the sensors on the ground. But we also use this as an opportunity to characterize the ground, because even boring information we had was at locations which are a little bit away from the bridge, not on the bridge side. So the UT team, they have deployed sensors and they conducted MSW, multi-channel analysis of surface waves, and it is along this line. So an array of 24 geophones was deployed, and you will see a little bit more. Okay, so this is how it looked like. Hopefully you can see these are all geophones. So 24 geophones, and Sledgehammer was as a source. So, and as you can see, very nice set of data despite of extremely heavy traffic. Something what was quite worrisome, what kind of measurements we are going to have on the ground considering the intensity of traffic. So in a moment, Brady is going to speak a little bit about what was obtained from those measurements. Moving to the next set of measurements which we have conducted and will conduct. Those are vibrations using, induced vibrations using T-Rex. So we will conduct tests in all 3 directions. I'm illustrating here on the swaying test in the out of plane motion. So T-Rex is going to be positioned at the center of us, at just above the pier. The second test, which is going to be tomorrow when you visit, is going to be with the T-Rex in the middle of the span. We expect that tomorrow the most exciting vibrations will be vertical, okay, as we apply vertical loading. But in addition to vertical, we will still have loading in the horizontal direction out of plane and also in the longitudinal direction of the bridge. Okay, what else you can see, and in a moment you're going to see how those sensors were actually placed. So there are triaxial geophones at all of these locations. There are accelerometers, and even more than what you see. How many total you have accelerometers?
That's 28.
Or 28 accelerometers. So they are placed along the curves, along the barriers. Then we have geophones placed on top of the pier and on the ground at 5 locations. 5, you may say, next to the footing, 5 feet, 10 feet, 20 feet, and 40 feet. And there is even one more vertical sensor 80 feet away from the bridge. There are also 2 3D accelerometers on the top of pier. Okay, so this is how it looked like when it was deployed. But to get a real feel for what T-Rex was doing, we cannot have noise.
No.
So probably here you can see the motion of the shaker mass movement. So this is now inducing swaying of the bridge. And the sweeps we did, we had 2 sets of sweeps. One was from 15 to 1 hertz. And then the second sweep was from 80 to 10 hertz. And the intensity of loading was varied from anywhere from 3,000 pounds to 21,000 pounds. So there were 6 or 7 levels of loading because we were interested to see whether we are going to start observing some non-linearity in the response. So this is right now vertical motion.
It's smoother than that, it's just jerking.
Okay.
Oh, the slope, my computer is slow.
I assume that you will show much better photos or video number.
Yeah.
Okay. So in addition to T-Rex, yesterday there was data collection using Thumper. So Frank is going to speak a little bit. Frank is going to speak. Maybe John is going to address a little bit about, after loading, a little bit about our sensors. So there were multiple triaxial geophones arrays. So you can see 2 horizontals and 1 vertical. And here you can see 3 triaxial accelerometer without 1. That's right.
Right.
Here it is only 2 directions. And so there were 6 geophone arrays on the deck, and I think altogether, what, about 14?
43.
Pardon?
43.
43 geophones. So it would be 14 locations plus 1 vertical. Okay, I don't have a photo of, I did not climb up there to place sensors. So, but there are sensors on the top of the cap, because what we wanted to do is we wanted also to capture what kind of transmissibility or transmission we get from the deck to the pier. I have already mentioned that there are geophone arrays on the ground, and as you can see, so there are 5 such stations away from the pier, from 5 to 10, 20 feet. Okay, and if we would like to say, so what are we trying to do with this project? Well, probably our guiding goal is, can we infer contributions of soil foundation substructure interaction on the overall response of the superstructure? The second is, and that is where John Levitis, Frank Moon are going to work, is like they have developed various procedures for structural identification of bridges. Can they extend it, which is also include the effects of dynamic soil structure interaction? And certainly what we would like, and we really hope that this is what I almost see like a pilot project, that it is going to succeed, so that we can say that at the end of the project we can say, yes, these NHERI shakers, when they are used in pretty high capacity but under controlled manner, that they can really be used in evaluation of, at the moment, the reason why we had selected bridge was simply because it was easy deployment. Otherwise, we would be very happy to go on a building. But what we would like to demonstrate through this, that these large amplitude forced vibrations can be used in the assessment close to safety level of the structure. Okay, there are a number of those who should be acknowledged. We certainly want to acknowledge NSF eager programs for supporting this project, NSF NHERI, for providing us opportunity to use mobile shakers, We are very grateful to NHERI for first providing us or giving us approval to go on the bridge. You know, we have been talking to various parties, municipalities, townships, and so on, to get permission to do testing and staying in the same circle. So finally, NHERI stepped up to the plate and allowed us to go on this bridge, and we are very grateful for that one. And finally, you know, as I said, it has been a wonderful experience, not just working these past 3 days with the team from Austin, but also just preparing for this testing. I would say that was a wonderful experience. So with this, I would like that now Brady says a few words. So what was processed the past night?
Great. Yes. So real quick, we'll try and go quickly. We didn't really know what we were going to talk about because we didn't know what data we were going to collect and how much we were going to be able to process. So as Nanette said last night, we were trying to process data and put things together in some slides. And I'm going to talk about the soil characterization, but also looking at some ambient vibration recordings from our low frequency seismometers, not just on the soil, but also on the structure. And I'll show you some of the results that we've gotten so far. And I'll try and go as quickly as possible so that we can maybe make up some time if the computer will run.
Maybe. It's a big file? It's not a big file. No, apologies. The computer is not. The computer is also we have a web live, so it's gonna be the first one.
No, you're right. Middle somewhere. Right.
I'm not going there. I'm just gonna do this. It was risky.
Are you going the right way?
Yeah, 8. Slow.
Okay, just see what happens here. Okay, so I'm going to be talking about the dynamic site characterization as well as some ambient vibration analyses of both the site and the bridge. In terms of the dynamic site characterization, Nanette already introduced what we did. We did some surface wave testing. It's surprising, especially for any older structures. Sometimes it's really difficult to track down even something as simple as boring logs. So you don't really know what the subsurface profile is like. So we did some non-intrusive testing, and this is going to be very brief. Essentially, surface wave testing, we're going to spread out arrays of sensors across the ground surface. We'll have a dynamic source. We could have used T-Rex or one of our other machines, but there's no space down there along the median. And we didn't, we already had to close down one lane, and that's expensive. So we just simply used a sledgehammer in this case, which doesn't allow us to go very deep, but still within the depth of influence, I would say, most influential of the foundation for this bridge. We then have to go through some processing of these waveforms that we record to get something we call a dispersion curve, which is a relationship between phase velocity versus wavelength or frequency, either one. And then from that surface wave dispersion curve, we then have to go through an inversion program process to get shear wave velocity versus depth. Now we want shear wave velocity because it's directly related to the shear stiffness or the shear modulus of the soil. And then Nat already talked about how that's an important parameter in this soil foundation structure interaction. You have to know the modulus. The soil is part of the structure. Believe it or not, the bridge is resting on the soil, and its stiffness and dynamic response is important. So we can skip through most of this in the interest of time. And I'll go ahead and just briefly talk about. So we did active source MASW testing where we have an array of geophones across the ground surface. In this case, due to the limited space, we only use 24 geophones. We'll use as many as 48 sometimes, and we'll space them out anywhere from 1 to 2 meters up to 10 meters. We'll have very long arrays sometimes. We usually hit or shake with our trucks in different locations relative to the array to avoid things like near field effects and get different wave propagation paths. And then a lot of times we'll deploy passive arrays where we'll have circular arrays of those low frequency seismometers, which allows us to pick up really low frequency waves propagating through the site. Okay, but in this case, we only used MASW testing. Here's the array, and Nad already showed that. We did 4 shot locations on either side of the array. We go through processing, 2-dimensional Fourier transforms. We take the waveforms, we transform them from time to frequency, and we transform space or the receiver locations, from the spatial domain to the wave number domain. So we do a 2-dimensional Fourier transform, and we get these beautiful color plots that look like this, where we can identify hopefully the fundamental mode of surface wave propagation and sometimes even higher modes of surface wave propagation through the soil layers. And from this dispersion data, then we have to go through a process of inversion to back out the shear wave velocity versus depth. We haven't done that for the site yet because that actually takes a fair amount of time. It's easy to generate the dispersion data. It's much harder to do the inversion. So what I can show you here is the data from the Hobson Avenue Bridge. This is the dispersion data we collected in terms of wavelength over here and frequency over here. So phase velocity. This is not shear wave velocity. This is Rayleigh wave velocity. Okay, so we have to turn this into shear wave velocity versus depth when what we have is phase velocity versus wavelength or frequency. The data was really high quality, which I was shocked because from the NAS descriptions, I thought this was going to be a relatively not a very busy road, and maybe from New Jersey, it's not a busy road. The bridge is not busy. There's a full-blown 6-lane interstate under the bridge, okay? And it's busy. There's a lot of cars going by, and it's really loud. But we got excellent data, but I was shocked at how soft it was. I couldn't believe it. This bridge is on a shallow foundation. 100 meters per second phase velocity. For those of people who don't know what that means, is that soft, Professor Stokey? Or is that, that's soft. That is remarkably soft. Professor Woods, that's soft.
Yeah.
100 meters
Lowest
per second.
I've seen is 80.
There you go.
It sort of goes along with what we see. Geologists overestimate the stiffness of rock. I think engineers overestimate the stiffness of soil.
So right near the ground surface,
They don't have any way to judge.
it's 100 meters per second. So if you want to know the shear modulus, you square that number and then multiply it by a mass density, and that's a very low modulus. And then we got pretty good data out to wavelengths of 10 to 15 meters, and then the signal to noise ratios dropped because of all the interstate traffic, and things started to fall apart. But still, we can extrapolate with some caution, and we can estimate VS30 just from this dispersion data. It's an estimate, okay? But VS30, for those of you who operate in the earthquake world, that's a parameter that we use often in the code for characterizing the site classification. And we can estimate VS30 from VR40, and it's about 250 to 300 meters per second. So that's the average shear wave velocity over the top 30 meters. That's a soft number. For those of you who are familiar, that's a site class D soil. And site class E is the worst soil classification. Unless it's liquefiable, then it's F. But that's a soft site, okay? Soft site. We did ambient vibration testing in the Freefield. So each one of these dots that are color-coded with different shades, a lot of them are kind of green, so we might have a hard time distinguishing them with this projector, but we deployed these broadband seismometers in the Freefield, about 30 meters from each kind of quadrant of the bridge, and then one here in the median. Again, we weren't able to do a lot of measurements here just because of the traffic and installing all of our sensors and stuff. But I'm going to show you what we got, our results from ambient vibration testing in the Freefield using these stations here. So here's a picture of this one down in this quadrant here, and you can see T-Rex on the bridge. This was yesterday afternoon. So just recording noise. This is kind of nasty, right? Doesn't look, this is an hour worth of data, but this is just ambient vibrations from cars driving by, from, who knows, really distant earthquakes, from wind loading. This is the vertical component, the north component, and the east component from one of those stations that we deployed. And if you take the ratio of the Fourier amplitude spectrum of the horizontal component, in this case the north component, and you divide that by the Fourier amplitude spectrum of the vertical component, we call this a horizontal to vertical spectral ratio. We simply do that division. We do that division on different time windows. This happens to be 30-second windows over an hour. Okay, so there's 120 time windows. We do that division, and we get something that looks like this: frequency versus H over V amplitude. So it's horizontal to vertical amplitude. There's a nice peak, and we get a fundamental frequency of the site. Now there's reasons for this. One of them is that one school of thought is this is the fundamental shear wave transfer function of vertically propagating shear waves, which have a high horizontal motion and a low vertical motion. Another school of thought is this is something to do with what we call Rayleigh wave ellipticity. So surface waves at the resonant frequency of the site, you'll tend to lose the vertical component of motion, so you get high horizontal motions relative to vertical. Regardless, we know that this horizontal to vertical spectral ratio provides a really good estimate of the fundamental frequency of the site. And we can use it to constrain the depth to bedrock when we do inversions to get our shear wave velocity profiles. And there's this kind of fundamental relationship where F naught, the site, is approximately the average shear wave velocity down to bedrock divided by 4 times the thickness of the soil. So if we know something about the shear wave velocity and the thickness and the fundamental frequency, all of these things work together to govern kind of the dynamic response of the soil. So here are some H over V results from the Freefield. You can see this station here on the north side of the bridge, and this one here on the, I guess this is the northeast and the northwest. And here are the H over V results from those 2 stations. And in solid line is always going to be the north component or the inline component. And in dashed lines are going to be the cross line or the transverse component. And that's relative to the bridge. So we always oriented our sensors relative to the bridge rather than to like true north, because we don't really care about true north. We care about what's happening relative to the bridge. And in this case, we get a very stable fundamental frequency on both sides. We also don't really see any difference in terms of north-south versus east-west or transverse versus longitudinal on the bridge. We can add in some more locations relative to these other Freefield sensors, and there's some variability there. The frequencies vary a little bit, but by and large, the fundamental frequency of the site around the bridge is somewhere between 2.25 and 3 hertz based on our ambient vibration recordings. So remember that number as we start then looking at what's happening with the bridge. If we look at the near field soil, so when I say near field, I mean, we missed a slide. What's happening here? So we deployed these stations also right next to the piers. And I'm showing them kind of on the outside that they were literally almost touching either pier underneath this central bend here. So we're looking at these 2 locations. If you take the horizontal to vertical spectral ratio of those locations, again, solid lines are in the longitudinal and dashed lines are in the transverse. Now you can see some differences in amplitude of the longitudinal versus the transverse components, but they're very similar from one side of the band to the other. So they're similar to one another, but the differences now exist in the longitudinal direction versus the transverse direction. Interestingly, you're getting a big response still at the fundamental period of the site, but the amplitude is going up, and then you're seeing some higher modes up here that are something to do with this soil foundation interaction, but they're pretty high frequencies. If you look at all the soil response curves relative to the near field soil, so the free field versus the near field, everything's still happening at that same frequency, the fundamental frequency of the site, at least here, minus this stuff that's going on at higher frequencies. Okay, what about the bridge deck? We deployed stations, also these broadband stations on the bridge deck here. I'm going to show some results from those. They were up here next to the sidewalk and next to the Jersey barrier. Here are the H/V results from the bridge deck. Why in the world would we do this on the bridge deck? Why take a horizontal to vertical spectral ratio on a structure? This reasoning falls apart. And as I was talking with Frank about this the other day, we've done this on ridges. We look at topographic amplification. This tends to work. This is the first time I've ever done this on a structure. So we took a horizontal to vertical spectral ratio, and we get a nice peak right here at 4.275 hertz. My theory, these are again solid lines, so they're the inline components. And that is very interestingly right in the same zone as the fundamental frequency of the site. Why? Is the bridge influencing the site, or is the site influencing the bridge? Something to think about. If you look at the transverse component, the horizontal to vertical spectral ratio, there's a little bit of a hump there, but there's also now this nice frequency popping up very close to 5 hertz. Remember Nenad's model where he said he was getting 4.74 to 4.64? So that's interesting. It's just some ambient vibrations, but processed in a very different way than I think structural engineers would typically process ambient vibration data. So that's kind of interesting. So why H/V on a structure? As Frank mentioned, well, the vertical modes and the horizontal modes are occurring at very different frequencies. And so when a horizontal mode is having a lot of excitation, normally the vertical mode wouldn't be. And when you take that ratio, it's just a way of normalizing it, and you get this nice peak that comes out, perhaps. And then this was the question, which I never cleaned up my slide. So that faux long, that's supposed to be F naught longitudinal, etc. But I think it's interesting to think about how is the bridge influencing the site, or how is the site influencing the bridge? And if the bridge is quite soft longitudinally, again, as discussions have taken place over the past couple of days, it's easy for the bridge to move in this direction because of the expansion joints. It's meant to move a lot. Frank said an inch, easily accommodate an inch of movement seasonal, okay, in the expansion joints, just the deck expanding and contracting. So the bridge is meant to move longitudinally. And if it's meant to move longitudinally and the site beneath it is resonating at a certain frequency, then maybe that resonance from the site is getting carried into the bridge deck this way. But it's not getting carried into the bridge deck so much in the transverse direction, okay, which is at a little bit higher frequency. And there's all of the soil response curves superimposed on the response curves from the superstructure. So this is a little bit of vibration testing that we've done, or processing that we've done so far. I think it's interesting to look at how the site is contributing to what the structure is doing, and to try and couple that movement together. I'm going to turn the time over now to Mung to show some very, very preliminary results from T-Rex testing.
Wouldn't the transverse, so this way, be softer than the longitudinal? I would have expected.
Frank?
Yeah, I don't think so. Mainly because longitudinally, the only thing that's supporting the bridge is the pier out of plane.
expansion drawings, isolated from the abutment. So like tomorrow when we go out there, if you stand across the expansion joints, we're driving it longitudinally, the foot on the bridge feels the vibration of the foot off the bridge. So the bridge deck and the pier can just slide like, now obviously at some point, you're going to get the back wall of the abutment, close off the joint completely.
But that surface, you're driving on, doesn't move laterally. That's longitudinal.
That's right.
So when you're twisting it, it's just because it's such a long thing that it doesn't have much resistance longitudinally. I mean, I would have thought the deck.
So
What does it look? What does the deck look like right in the middle? Is it two pieces as well? Is
No,
there one there? Is one
One
continuous
deck
all the way
with
across?
a pier, and it's just moving like this, very
It's
small,
like a single degree of freedom oscillator in this direction, very much.
with rollers on either end. Basically. I don't know what these bearings are, probably.
But it also, roller, you're right. A long member, even if it's fixed, I would think, that's interesting. It's interesting to think about.
Yeah.
No problem.
Okay, we shake in one location only, and we shake it vertically, horizontally inline, and horizontal cross line. I'm not going to talk about horizontal cross line only because of the time that I have to process the data. Okay, we shake it from 15 hertz
Now, was this the
to
best
1 hertz.
looking data also?
Second?
Was this the best looking data also?
They all look great.
Oh, okay.
There's
Very
so
good.
much data.
So, yeah, we shake it from 15 hertz to 1 hertz, and also shake it from 80 to 10 hertz. I only look at 15 to 1 hertz right now. So here's roughly 15 hertz, here's roughly 1 hertz. You see it resonated right there. It's roughly 4.57 hertz. If you look at, oh, I'm sorry. I also need to show you that it does shake at different amplitude from just the noise at 3,000 pounds, 6,000 pounds, all the way on to 21,000 pounds. We start to get scared, so we stop. That's just the noise though.
About 60% of full force output based on the readings that we were getting, and everybody was huddled around and said, this is good. This is good for non-destructive testing. But we had 40% more that we could have went. So
Okay.
So
So,
can you
yeah.
go back to the other one? Are you telling me the peak there that we see at 25
don't-
seconds or something like that? No.
Say again?
Yeah. Where's your 4-point?
it's
That?
hard to see that frequency.
Yeah. So I show you the frequency in the frequency domain here.
Okay.
So this is from 1 to 10 hertz, and this is velocity in second, but its FFT is the linear spectrum, so it's not. It's assumed that if you do FFT, it's gonna be smaller than what actually happened basically for those cycles basically. I'm not gonna go into detail. So this is, you can see if I draw a straight line there, you see this, the response curve shoot to the left. It does get slightly softening. This is the joke on the top of the deck, on that side.
Okay, so in other words, you're going, at the bottom the peak lines up, and at the top the peak is to the left of
Yes.
okay.
Yes.
Something.
Without shaping anything more than that. Holy mackerel.
Just to give you an idea, this is the theoretical force output of T-Rex, and then the peak velocity we measure going, we don't know. But this is not quite right. This is just noise. So this curve is this stiffness not right. So yeah.
Do you have an idea about the connection and the subtitle?
Frank, you want to answer that question?
Yeah, you see it. Yeah, so they're probably steel bearings, the old style. These are not the elastomeric ones, right?
Right.
They're the old style steel. So every girder is connected to a pin, connected to pier cap. So that is fixed connection. And then at either abutments is the expansion. So it sort of expands out in the back.
That was just
So you want,
why you want to get a more kind of a yielding behavior as you increase the force.
you want motions above and below, just to see what that bearing does do.
Yeah,
To the motion.
we have all those. So we haven't looked at it. I don't know.
I looked at the ones below.
So, yeah, that's nice.
We'll be at the restaurant, but
So, moving on.
Oh, can I just from, at least I would,
One more.
I hope that we all agree that if you look at the peaks, that it is shifting towards lower frequency, which means that the system is softening as we increase loading.
And you can see that about,
Now it goes back to.
this is log scale, so it's go about 100
you
times
get it
higher.
back, you get it back.
Yeah,
Okay,
go
good,
back.
Go back
good.
to, if you go back to low frequency.
No amplitude.
Low amplitude.
It goes back.
Goes back.
Yeah.
We check that.
Okay,
You
so
can see it's elastic.
Well,
Non-linearity or elastic?
you know, well, that's your story and your state. Yeah, you got it.
we got a lot of data,
That's for today.
and I have a Jupyter notebook to show you the different sensor, first different sensor. You can look at it later on, but for the sake of time, I'm going to show you two sensors to emphasize the importance of using T-Rex. This is two vertical components, two vertical on both ends of the bridge deck, just vertical. So if you do a transfer function between them, you'll see that it's supposed to be almost the same amplitude if it's assuming pure rocking, right? And the phase should be 180 degrees out of phase because they're doing pure rocking. So that's the benefit of T-Rex. You can actually see the phase shift. I can plot them out. And there's something resting there, so something happened there. I don't know what happened, but in theory, rocking.
But now wait, it's always doing coupled rocking and sliding.
Yes.
Because you've got these
Yes, yes,
forces at different
Yes.
points, but still, it's going to be dominated by the
yes.
rocking.
So if you do noise, don't get phase. That's the point of our course. Thank you very much.
Well, I bet you if you were given enough time and money, you could figure out what's going on with that phase.
Yes, you
know,
could.
it looks sort of
That,
random, but
No, not the noise one. That if you get from ambient noise, you can't make out of it. But if you get from the T-Rex shaking, then you can go phase by two joint, two sensor, look at the phase, figure out how it's actually shaking basically. Okay.
But if you didn't create any really nonlinearities in the soil that changed the soil, I would expect it to come back. I mean, I wouldn't expect it so much to be nonlinearities elsewhere. Do you see it in the damping? Mung, do you see damping increasing
No,
with amplitude?
no, not particularly.
We haven't had a lot of time.
Yeah. Yeah.
Scrutinize things. There's a lot of sensors.
So-
John is going to talk about some
Yeah.
stuff in a minute too, but I think people are just very literally scratched a very minimal surface of a lot of.
So just
There is a lot.
running through the slides for you.
In the foundation, you'll have to see what you can, if you come about.
Again, this is noise.
Start looking at strains or something. What kind of strains would be
It's
needed
T-Rex.
to create a phase shift like that? Let's say if it came from the foundation. To see if it looks like it's still in the linear, reasonably linear, so it's going down a bit, which won't hurt the soil.
Yeah.
Sorry, can you go back to what you just asked? There's a
Oh.
conversation going on about this.
Which one?
I just want to point out that what Mung was showing very briefly is Jupyter notebook that he's created. That is Jupyter notebooks is what he was saying for free open source, and you can use it just like MATLAB, so it's free. Design Safe supports Jupyter notebooks, and he's created a notebook to analyze some of this data, and this is the sort of thing that we'll pass on to the Rutgers crowd, and they can continue to use it and adapt it to their needs. This is what we would do for users, but this is something that potentially they could post on Design Safe so that others could see how they analyze data for these solutions.
Yep.
Open access to data processing.
So, and then I tried to convince Joel Conte at San Diego, and we submitted a proposal on bridges with T-Rex. Probably 2004 or 2005. And I think I still can see the smoke from it going down from the reviews. But this is really pleasing to see because our tail feathers were burning from those reviews. And so it's nice to see this data.
All right, so I'm going to talk about, mainly in the interest of time and just getting something mildly conclusive or a look at it. I took a look at the two triaxial cells at the top of the substructure, right? The pier. And so you can see in the lower right-hand corner here, this is the one on the east side. And what I'm looking at is the transverse motion. There we go. Due to this input, this is in the frequency domain, and this was just from the trigger signal that was sent to the shaker. And I just want to get an idea of the force levels for, this is 1 volt, 2 volt, 3 volt, and 4 volt, which I believe it's around 6,000 pounds per volt. So
I can go to 4 volts. I only go to 3.5.
Close enough.
Yeah.
all right.
Especially when you're processing.
Yeah. Okay. So this is our force spectrum. And then this is, the top would be the 1 volt time history. This is acceleration, and units are in G's. The bottom is the maximum amplitude signal that we put in. So we can see these are scaled similarly. So we can see kind of order of magnitude the responses that we're getting. And these are all of the accelerometers, both superstructure and substructure. So just order of magnitude comparison here. And now what this is, it's a little busy, but we have our 4 different loading cells, or 4 different loading amplitudes transversely, and this is for each transverse measurement. So we have a pair here, a pair here, a pair here, and a pair there. And so we see very consistent measurements between the 2 triaxials. And we also see, so this is on a log scale, the y-axis is the log scale. If we remove that log scale and just make it linear here, we can see the shift in frequency due to the magnitude of the input. And so we start off at the low level at around, now this is just peak picking here, but this is about 4.7 hertz, 4.712 hertz. And at max, we get around 4.614. So it's about a 1/10 of a hertz drop from our lowest magnitude to our max. These 2 peaks were interesting, having these pairs of peaks going on. And so what I did then was I looked at, so we have our 2-span continuous, and I looked at a vertical accelerometer on an exterior girder above at the center of one of the spans, right? So this would be the maximum amplitude for a torsional mode, and this is vertical. And what we see, it's plotted here in red, and all that I'm showing is the maximum load level that we went up to. But you can see, well, what's interesting is these frequency measurements that, as a structural guy, first thing I think is, oh, okay, this is first bending, this is first torsion, what's going on next? These are right around the 2.5, 3 hertz that we're seeing, but we also see a major amplitude right in between of those 2 peaks that we're measuring. And so, I mean, I don't know, but.
So you have the bridge as one continuous deck.
Yes.
That's because there's no joint here.
Continuous steel also.
One continuous. Because I see a bow and arrow or something. I mean, I see the flexural. Here's T-Rex as an arrow in the middle of when you're moving this bending.
Mm-hmm.
And so that's what you're calling the first bending, I guess.
No, the first bending would be vertical.
Right. First bending of a vertical mode. So these be both the spans.
I think
Maybe
bow
I'm
and arrow.
confused.
Yeah, I think the bow and arrow probably doesn't quite occur like that because there is a lot of play transversely in the abutment bearing. They put what they call an alignment bearing in there, but it has an 1/8 of an inch plus or minus. I'm not so sure we're bottoming that out. But if we did, the stiffness of that deck in its own plane would be very common. So I don't think we'd be seeing that at like 4 hertz. I think that would be.
But you have enough sensors out there to check that
Yes,
when you get into the data.
absolutely. And so I don't know if you recall the animation here with the rocking, and this is exactly,
That'd be complex motion. to look
Yeah.
at.
and so, okay, the sensors that I'm showing here, this red one is, it's in this dead center of one of the two spans on an exterior girder. So it'd be maximum amplitude for a torsional mode. And then the other two are the east and west transverse measurements on top of the pier. Yeah, on each end of the pier. Yeah, on the pier cap. Yeah. And so this is pretty consistent with the rocking motion that we were seeing, or the sway motion. But what I find interesting, and I don't know, maybe someone can comment on it, is this occurs dead center of these two peaks that we're observing. That we're also observing the geophones, I think, if on that plot there.
What Mung showed and what John is showing were processed two different sets of instrumentation. Mung was working on the geophones. We didn't know what John was going to present. John didn't know what we were going to present. We both just grabbed some data and started processing. But it's interesting to look at how similar the little bit that we did,
Right.
and how it looks. But we didn't look at any vertical motions at all.
And so that was about as much as I was able to get into. And then what I was doing here was just, okay, what's kind of the next steps here? One, we would incorporate more averaging because we have so much data, we can clean this up. Two, I want to take so these were just output signals. This is just due to the response. So if we put a 2 hertz, steady state load on this, we would show a big spike at 2 hertz, and it's not normalized to the input yet. Although the input was pretty flat over this frequency, so I think the results still stand. But we would want to go that next step. And then I'm very curious what the superstructure is doing during all of this. And so we have a instrumented superstructure with enough resolution where we can get a good idea of what's throughout all of this. So that's about it.
So we don't try to estimate force levels that we're applying.
We calculated on the base plate mass around.
Okay.
We did that.
And we've never tried to we've never built our load cell calibration
We do
system
vertical.
on a pickle, did we?
We did vertically actually close enough. But by about force output is based on a set around to not on the base where the situation plays, so they are quite noisy compared to the geophone signals.
I'm just thinking about what we might do to help what you can record and how clean it is or how precise it is. It's a little bit like when we were shaking the ground and trying to predict cyclic stress levels at depth. There were things in between that caused complications, nonlinearities. Thank you. When you showed your plots, I thought the waveform started to change a little bit around resonance, in the resonant part of the thing. Why is there such a big jump between 1 and 2 volts to start out with?
It's likely that at the low amplitude you have friction. You have to overcome that first for you to get started.
I thought the same thing, by the way. But again, 1 to 2 is doubling, and then 2 to 3 is not doubling. So
yes, that's
but
correct.
It still looks like the form changed a bit.
That's detail.
Well,
I guess
okay.
we need look more into it. So should we
You just started it, so.
take a break or should we keep going?
I think we,
Notice Frank has his presentation.
we want to listen to Frank. And we have some flexibility in doing the tour and what time we're doing the tour and stuff like that.
Yeah, so I just been texting one of the students that's setting it up. So, we can either skip my talk, I can give this, and then we go up there at like 5 instead of 4:30.
So fine with us. I mean, I think most of us are here to
Yeah.
Yeah.
listen. And so you do what you feel comfortable with in terms of balancing your talk with the tour. We're having you just go off to the right here. So.
Okay. So this is a really general talk. What I wanted to do was maybe present a little bit, at least from my perspective, on how global structural assessment is done right now from a structural engineering perspective, at least for bridges, which is an area that I've been working in. My background is actually in earthquake engineering. I haven't done much work there for a few years. But one of the things that was really interesting today is hearing, I feel like I should have been a geotech, because you guys have a lot of the arguments that I have with my structures colleagues, seems like you guys have already figured out. One, that scale, number one, is really exciting. That's actually what got me into engineering to begin with. Two, that field testing is really where you learn a lot of things. I did a lot of laboratory testing, but field testing is sort of, I think, the where research should be undertaken. And then third, that you can't just take a measurement and use the measurement. You need a model to help you interpret what you have just measured. And these may sound like they are obvious. I don't think they're necessarily universally accepted, at least in structure. So I've been making this argument for a long time. I don't think I have to make it with you guys, but what I wanted to do here was first talk about the difference between what I would call instrumentation and global structural assessment. You can call it structural identification, SHM. There's all sorts of different terms you use. But this is a project that I worked on a few years ago. This is I-495 in Delaware. Somebody came and dropped about 4 million pounds of dirt right here to store it. And the bridge tipped 2 feet to the right and 1 foot vertically. It's about 60 feet tall. So that afternoon, we actually went there and put a bunch of tilt meters on there, right? So this is an example where you actually don't need a model. They wanted to know, did it stop tipping, right, number one. And they wanted to know when they removed the dirt, how much did it come back. This, in my experience, is a very rare problem where a sensor actually solves it. And so this is what the data looks like. It tipped roughly 2.6 degrees if we assume that it was vertical before the tipping, and it came back roughly 0.25 degrees. This is when they removed the dirt. And so they actually replaced the entire substructure. I actually borrowed rebar cages from the Tappan Zee Bridge and paid them back so they could do this. They replaced the substructures in about 2 months. But this is a very rare situation. Generally, we have this fundamental challenge. And this, I don't think, is as big a challenge for laboratory testing as it is field testing. But fundamental challenge is you can measure certain things, right? But what you measure is not what you need. So the things that I care about, where's this thing? Oh, there we go. So the things that I care about, maybe capacity, I cannot measure out in the field because I have to break something to do it. Right? I can measure it in the laboratory. But I can measure out in the field or strain, acceleration, displacements, all sorts of things. And so I have to do this translation. So what you measure is not what you need. What you need, you can't measure. And we have to remember that just because I can measure something doesn't mean it can tell me about what I care about. Right? There is this very interesting translation that has to occur, and it is structure dependent, and that's why we need a model. We can calibrate a model. We can then try to predict some of these things. I noticed that you use millions of models for an inversion. We do the same thing because there are many, many models that match the data, and I think they all have to be considered as long as they're plausible. So this is not a clean process, but I think it's a necessary one. So why is this so difficult? I won't go through all of this, but our structures are unique. We have very large and uncertain intrinsic forces. They're non-stationary, so they're different in winter and summer. They're complex. We have stick-slip mechanisms all over the place. Right? If you go into mechanical engineering, where there's a lot of work in this area, their systems are way simpler in many cases. An airplane is a lot easier to model than a large bridge. We have complex boundary conditions. You guys are all geotechs, you know about that. And our scales are very long. large, not only spatial, but also timescales. Right? We instrumented the Brooklyn Bridge a few years ago. That was built like the 1880s. That's a long time. It was completely reconfigured in the 1940s, and these things have been around for a long time. So assuming a standard connection performs the same everywhere on the bridge is not actually a generally very good assumption. So there's this general framework, right? You review the what you can learn about the structure, you build some sort of preliminary model, you look for sensitivities of what are the things I can measure that can teach me about the things that maybe I can't measure but I want to know. Use that to design an experiment, you process your data, you try to match these two things. There's a lot of different ways to do that. It's really messy, there's no clean way to do it. And then you can use your model to hopefully learn something, right? Sounds great. It also could look like this, right? If you don't observe or conceptualize the problem very well, it really doesn't matter if you have you carry out your experiment really, really well. You didn't design it properly, right? So it can certainly be unstable. So before I get into just a few quick examples, just to sort of, the goal is to maybe provide some context as to why I'm excited about something like T-Rex, because it fills a gap, a specific gap that I've seen in structural testing. But there are these distinct challenges, right? We have a lot of signature bridges in the Northeast, right? So these would be, you could roughly say $500 million, $1 billion replacement cost. They rarely get replaced. We're replacing a few right now, but in many cases, the owner wants to indefinitely preserve them. So they don't mind spending money on instrumentation, on learning about the structure, but they do have to preserve it long term. And then you have the opposite problem where you have 600,000 of these common bridges. Nobody really can spend a lot of money on any one of them, but as a whole, they sort of constitute a pretty significant asset class. And the other thing to know is owners of these types of bridges generally have lots of money. So for example, the George Washington Bridge probably brings in north of $1 billion a year. I mean, it's the most heavily traveled bridge in the world. A bridge like this brings in no money, right? So states and counties that own these bridges are constantly struggling for funding. Owners of these bridges generally are not. It's a general statement, but it's typically true. So what I would call the common approach, and this probably goes back 30 years maybe, is to use ambient. If you want to learn something about these bridges, you go out and put tons of accelerometers on them, and because they tend to be very long, you get traffic over, you get a lot of excitation, and you process that assuming some sort of broadband white noise input. You can get frequencies and mode shapes, and you can update a model based on that. Yes?
So for us, when we went down the plains, we're arguing that if you also knew where the source was, in addition to the motions, you got a lot more out of your analysis than just saying it's random vibration.
So I
don't know that that's true.
I think it's true. I think there's a couple things. One, this is output only. Anytime you can get input, output, I can know more about the system I'm trying to characterize. Second, the magnitudes of what the excitation is are very small here. So when you have stick-slip mechanisms that I had talked about, which are all over the place, you're modeling a bridge in the stuck condition, right? Earthquake comes along, it's not stuck anymore. So the system that you thought you were learning about is actually different than the system that's going to experience the earthquake. Another thing, and it's a little bit of a tangent, but when we were doing the Brooklyn Bridge, a lot of what happened was remapping of New York City seismic maps. And so everybody says, oh, we got to do seismic assessments of all these old bridges. Well, with the Brooklyn Bridge, they have these old masonry towers and pretty flexible superstructure system. And the consultant that had been hired to do the seismic vulnerability assessment needed some data to update their model. And so we had put sensors, all over
the structure. We were giving them the frequencies and mode shapes of what we thought the important part of the bridge was. That's what we could measure. Traffic was exciting the superstructure. But then something interesting happened. Right before we took the sensors down, there was a micro tremor. And all of a sudden, the modes of the towers pop up. We'd never seen them before. All we saw was the modes of the superstructure being reflected in the tower. Superstructure swaying, towers are going along for the ride. Right? And you might think, just like you said, what's driving what? You might think, oh, those are the tower modes. Those are not the tower modes. Those are a reflection of the superstructure mode in the tower. And we would never have known it if the micro tremor didn't happen and now the excitation came up to the tower. So now if you had put T-Rex right over the tower and shook it, I think you could learn a lot about the tower.
But we also wanted to put T-Rex in the median and have it, like Patricia talked about with the structure, have the input come up through the ground.
Yeah.
And see what happens. That's what you're talking about.
Create the micro tremor. Okay. So in any case, this is pretty common. We do this on a lot of bridges. It's almost standard practice now. So you get a contract to do some retrofit assessment, whatever. We've been working on these bridges. We've also worked on bridges, Middle East, in Hawaii. We have been doing the Ford Island Bridge out there. So
we have a reduced rate for working in Hawaii.
Yeah. So there's a couple other things I wanted to point out, though. There are limitations in that. One is that, as we said, you don't know the input. The other is that the excitation is very small. So what I did a few years ago is we started looking at what if we use, so this is my third, right? We have impulse, we have steady state, then we have temperature. It's very slow, right? But you can take data over years and you can get cycles. And what you're looking at here is actually the hysteresis of a friction bearing that is changing with temperature. And I can model the temperature pretty well. Right? I also can model where the sun is in the sky. It turns out that's one thing that is almost deterministic. You know exactly where the sun is at any given time, right? And so you can simulate this, and then you can calibrate models to this. Right? And one of the things that became really fascinating is going to play. Maybe it won't play. No, it's not going to play for some reason. In any case, if you plot for a few years of data, the temperature, the displacement of the expansion bearing, and any strain that is within the longitudinal load path of the structure, if you plot that, what you get is a flat plane in three-dimensional space. And you can derive that plane. Turns out that in order to do that, you need a stick-slip response at the bearing. And if you don't have any nonlinear, you don't get a plane, you just get a line. But that plane is very sensitive to any changes in the system itself. So if I lock up the bearing, if I fracture a member, if I soften connections, these planes change. And we looked at a number of different damage scenarios for a particular bridge, and you can see the sensitivity, right? Hundreds of %. If you look at the very common vibration-based sort of damage detection, it's almost completely insensitive to all of these things. Right? Here's the problem, right? So the advantage of this was we knew the temperature, so we knew the input, we knew the output, right? So we could really get a good handle on our system. The second was that the forces are enormous. Right? If you go put a strain gauge on a bridge, the largest force you measure is when the sun comes up, right? And it can be, you know, several KSI of stress. Right? We're not talking about noise level here. Way more generally than a truck that drives across. So we had really good signal to noise. We were overcoming any stick slip. The problem with it is we need a lot of data. So let's say your bridge damages. We can tell you in about a season, because we need to see those, all of those temperature cycles before we can start to say, oh, this plane has changed. Unless for some reason it jumps off. But this seemed to me to be sort of a slow version in some ways of what T-Rex can do, which is it can clearly, based on what I saw the other day, clearly push these bridges into the nonlinear. Right? which is what we need to do, right? That's what happens with temperature. So, based on this, they actually did, we did instrumentation. I don't know if you guys are familiar with the Bayonne Bridge, but this deck is I believe, almost gone. They've raised it 65 feet here, so they could get the new big post-Panamax ships underneath. So it's a $1.2 billion project, and they didn't even get a new bridge, right? They just raised it. So we also do some monitoring. So this is another sort of, I guess you'd call this static excitation. This is a movable bridge. It's actually a bascule bridge. It's the third largest bascule bridge in the US. And so we have some cameras out there. You're riding up on this. And what you're seeing here in response, which is pretty significant, that's 7 KSI of stress, starting at 0. That is changing the direction of gravity. Right? So vast majority of stress in large bridges is dead load. And so when you start moving it, basically changing the direction of gravity, you can really impact its stress levels, and you can see we're getting ship that goes underneath. We built this system to monitor this bridge while they were replacing the grid deck, because they had to make sure it was in balance. We wanted to sort of play around with some construction monitoring. And one of the things we found, which was quite interesting, is this is back 7 years ago now. This is what it should look like, right? And then one day, this is what happened, right? 18 KSI change stress, about half the material strength. And we were able, through modeling, to trace it to actually a connection slip, which we then traced to the contractor not following the proper procedure of drilling out a rivet, putting in a bolt, tightening the bolt, should yield the bolt, doing that for this entire connection plate, and then that night they can come when they close the bridge, loosen all the bolts, throw the old connection plate out, put a new connection plate in, tighten the bolts. During the day they didn't tighten the bolts, because at night they didn't want to have to take them. And then the plate slipped. It dumped. Fortunately, in this case, which is why we measured such a drop, is there was a completely redundant truss. So it just basically went from one truss to the next. So a huge drop of force. And of course, we alerted the contractor. And the interesting thing is they kicked a couple cameras into the water on accident, right? But it wasn't the camera. That's the interesting part, right? It's not the cameras. We didn't see them not tighten the bolt. You can just measure. So some things are easier to measure than to see. So that's sort of some of the things that are going on with signature bridges. Here's the other problem, right? There's 606,000 short to medium span bridges. You can't see this, but this is to scale. That's the number of signature bridges in the US, right? So it's a small portion. Now they are 1,000 times more expensive on average, give or take. So they're not negligible in terms of the dollar amount, but in terms of the sheer numbers, they're pretty small. And here, people really are not using any sort of sensors. Right? And that's one of the things, when I said I should have been a geotech, I think geotechnical engineering, at least from a civil engineering sense, at least recognizes that you need to go out and take data from the field. Right? I think in structures, we believe our models way too much. And it's like pulling teeth to get somebody to go and put a simple sensor out in a structure to say, is your model even remotely close? And so here, you've got about 60,000 bridges that are posted for legal loads. So they basically say these cannot take the legal loads that we allow on our roads, 60,000 bridges. But yet, only 600 have ever been load tested. People aren't finding load testing as an attractive sort of cost benefit. They're not seeing value in load testing because they're not using it. All of these 60,000 bridges could be candidates for load testing to demonstrate the capacity. And so let me skip this. So this was part of a NIST project, and we'll do a demo of this actually with when we do this tour. But this is something, actually, John's PhD is on this system that he developed. And the idea is an impulse. So we bring it out to the bridge, deliver an impact. It's a pretty much completely reconfigured falling weight deflectometer for pavement testing. But you'll see in a second, we actually catch this. We capture the force in a little different way, and we group this with a bunch of accelerometers that are on the side of the bridge. So we can rove this impact, which delivers about a 30,000 pound impact between about 0 and 50 hertz. So we induce a free vibration response, we capture that, so we stitch all those impacts together, we get frequencies and mode shapes, we can update models, we can do ratings. The idea here is to do it within about 30 minutes. Right? So the faster we can do it, the cheaper we can do it, that means the more bridges we can do. Now I can start looking at how bridges relate to one another. And so this is the system. Oh, a little slow, the video. But we'll see this, so I just want to show one thing. So these are just, everything's pretty much pneumatic except for the lifting of the impact carriage, which I think is still hydraulic. So it seats, you can't see it here, but there is a seating plate here that's got a series of load cells underneath it. This is an impact carriage that gets lifted and dropped. These are fast-acting actuators that chase it and catch it. So we get one big impact, and then we get a nice free decay. And what the data looks like, there we go. So this is our thumper testing, same as your thumper except without the U, right? And this is multiple input, multiple outputs, right? So we have fixed sensors, we're going and impacting at different ones. That's what we would consider the gold standard. But if you're looking at the modes all the way up to some of these higher ones, we're starting to get a little bumpy there. But we have very good comparison. Right? We're generally within 1% of all frequencies. And the mode shapes, if you guys use these modal assurance criteria, MAC values, if you're familiar with those, we're generally north of about 0.9, 1.0 being perfect. Right, and we've done a number of bridges. These are, I think, 10 bridges, 12 bridges that we did in the Northeast. And what we're doing here is plotting the bridge, first fundamental frequency versus span length. And so these are all different bridges: pre-stressed concrete, steel, and steel continuous. A lot of people thought, oh, steel continuous are going to be stiffer. Turns out they're more flexible. Mainly because under the first mode, there is no fixity. That continuous point is actually an inflection point over the pier. So I think we're actually systematically creating less stiffness in the continuous bridges, even though bridge engineers will tell you they're stiffer. They're actually not.
They made a tweeter into a woofer.
Yeah.
I mean, they got the big diaphragm versus the smaller, so to speak, and you change the frequency.
Yeah, exactly. And so we've also created, and I won't do too much with this, but I mentioned we need to have a model to interpret things. Well, if we're going to speed up the data collection, we also have to speed up the model. And so we're pulling information from the National Bridge Inventory that has a database of certain types of bridge sections. We're then trying to reverse engineer to the best of our ability what those girder sizes are based on the codes that were used to design them. Of course, if you have that information, that's great. A lot of states do not have that information. But the nifty thing here is the ability for our MATLAB code to talk directly with a software called Strand 7. So anything you can do manually, you can also do in an automated manner. So that was real-time creation of a model. And once you've created your model, you can then go ahead and update your model. And so we're now trying to look at the frequencies and mode shapes of the model and match those to the frequencies and mode shapes that we've measured on the bridge, and change things like the connection stiffnesses between the deck and the girder, and the bearing stiffnesses, whether or not the barriers are participating, and all sorts of things that are very uncertain. We can now update. You can see some of the parameters changing, and then they start to flatline. Right? This makes this seem like a very simple process. It is very non-unique, right? So there's lots of solutions to that problem, and then you can do rating. Right? So I'll skip this. So what I wanted to do now, before this is sort of a lead up to the tour, we can maybe have a discussion there because I know it's getting a little late. I wanted to give you a brief introduction to the Beast Lab. It's a pretty unique facility. We're very proud of it. We haven't quite used it yet, but we're about to. And so the idea here is one of the problems with bridges, believe it or not, is that they take a really long time to deteriorate. Roughly about 20 years before we start to see any meaningful deterioration. You might not think that's a big problem, but the problem is if I change something and I do something new, it takes me 20 years to figure out if that was better or not better than what I typically do. And what we see it with New Jersey DOT, New York State DOT, all the DOTs, they try things all the time, once, try them. And then they leave the bridge out there. And so there are bridges in New Jersey that are twin bridges. One has epoxy coated rebar and one has stainless steel rebar. Because somebody in 1994 decided, let's run a little experiment, right? And that experiment is now 23 years old. The jury is still out on which one, right? So the key is to accelerate this feedback loop. That's one of the reasons why bridge engineering today is no different, really. Some people may argue with me, but I would say it's no different than bridge engineering probably in the 1960s-ish, right? We have slightly different materials. We have different code methodologies, but at the end of the day, they produce very similar bridges. Because we don't have any sort of innovation, because we can't figure out if things work. And so just to give you an idea, this is 10 years ago, right? What's interesting is the iPhone was out 10 years ago. It was not the best cell phone of 2007, however. This one was. And 20 years ago, the big breakthrough was the internal antenna. So today, bridge engineers, sort of in general, are using technology from 20 years ago that they think they know whether it works or not. That's equivalent to walking around with a cell phone that has an internal antenna and bragging about it, right? So this is what we did. We built a laboratory that has a very large environmental chamber. It can accommodate a 50-foot by 28-foot superstructure. It can be up to 5 feet deep. We have, this is wrong, this is actually only 18,000 cycles a day, but we have a rear carriage of a tractor trailer that can run back and forth. It loads it up to 60,000 pounds, which is roughly double the legal load of the rear carriage of a tractor trailer.
So that's accelerated loading facility, is what your pavement facility?
Yeah, bridge, not pavement. It can cool from to 0 degrees Fahrenheit, which is really cold, all the way to 104. We can put precipitation on there, de-icing chemicals, and we can measure lots of stuff. And so this is, you guys had an animation, we have animations too, because we haven't done it yet, but putting the bridge specimens off-site and driving them about a quarter mile to the lab. The first one will be built in the lab, however. But basically, the lab opens up. All of the environmental chamber and the loading are on rails, so they can slide open and close. That can be located at any location along the bridge width. And here we go. So we can, I think you were right. This is, the video is a lot smoother than this, but I think it's just the fact that we're broadcasting this or something. But yeah, so we get the live load. So we're getting the live load, temperature, environmental, and we're getting the winter maintenance. Those are the sort of the 3 keys to bridge deterioration. The big question is, how do we make sure we're balancing these, right? We know if we just throw salt on something, we can get it to deteriorate. We want to balance them so they're somewhat indicative of what a bridge experience is out in real life. If you guys have heard of the long-term bridge performance program, here at Rutgers, we're involved in that, so we're also engaged in going out and taking data from a large population of bridges out in the field. So that's what we're using to try to tune this. And Nenad, we'll run a demo of this as well, has created what is known as the Rabbit, the robotic assisted bridge inspection tool, which has 5 different types of NDE probes on a autonomous Rabbit. We can take it out there and basically scan weekly even here, so we can identify when deterioration begins and how it progresses. addresses. So that is all I have. So yeah, questions, comments. Better.
So, did you guys screw up in your testing of the bridge the last couple days? Because you should have started at a much lower level to see if you could detect the stick before it got nonlinear or something, where it stayed constant and then broke, or however you want to phrase it. So, I mean, you just alerted us to a point that we didn't think of, but that we experienced with T-Rex, because if you don't give it enough force to start out with, it sticks. It's
So
move.
right, and this is the big. I forgot to mention it. Our big problem with Thumper. Right? We've done this for DOTs. We're trying to get it out there into practice so we can start testing more and more bridges. The biggest criticism that we've had is that it's not enough load. Because when you're rating a bridge, you're going to rate a bridge generally for, I don't know, at least a 100,000 pound vehicle, right? I'm putting on a 30,000 pound load that occurs over 0.05 seconds, right? And if you put strain gauges on there, you measure almost no response. It's spread throughout a lot of different frequency levels. And so the big question is, are you identifying this bridge, updating the model? Is that really the same system that carries the truck? Right? You guys have T-Rex out there moving up and down harmonically, 60,000 pounds. Nobody is going to argue that, you know, we have some mechanism that in fact, you know, is not going to be there. So we don't want you to rely on it, right? A big one is a lot of bridges were designed non-compositely. So the girders and the deck, they don't design them to work together. This is common practice in the 50s and 60s. So they say these things don't work together. In many situations, for example, we've tested bridges where we put 600,000 pounds of truck on a bridge, and it was designed to behave non-compositely, and wouldn't you know it, it behaves compositely. Because there is such a huge area of bond between the concrete and the steel, it doesn't break free. But even if we show them that with our Thumper, they will not believe it. But if you showed them that with T-Rex, because of your force levels, I think they would believe it.
So, if you put our Thumper, a little different spelling, we could start out with vertical or horizontal loads of a couple thousand pounds, can't we?
Yes.
So we could be in the stick zone easily.
Oh, yeah.
And
our Thumper is probably always in the stick zone. We can do that really quick.
But we could march along in that zone, let's say, and have multiple measurements so that we would prove that everything was in the stick zone, let's say, nothing changed. And then you come with a bigger machine to try to go out of the stick zone to see if, in fact, that's what you're doing. We didn't think anything of that. We always think bigger. Not going from one zone to another.
And I think that's, I mean, that was sort of the heart of NHERI's project here.
So what you did to me is you just had an I1 model, the linear. So Bill I1 and his hysteresis loop. So he's got a stick zone, it's elastic.
Yep.
And then it starts changing as you go further out. And that's interesting that that's maybe what you want to come up with.
Yeah.
You should be able to back that in too.
Yeah.
So we did the Thumper test on the bridge.
I'm talking about a different Thumper.
Oh, no, well,
Yeah,
I'm saying,
we did our low level.
we know the stick zone.
Okay, but I'm using the same frequencies now. I mean, I'm not changing anything other than the load level. I'm putting a constant. So to me, it's involving the whole system, where your stick zone might not involve the whole system because, like you say, it's a short duration. No, we're running a steady state test.
Right.
Same wavelength.
Yep.
But just very, very low amplitude. So I mean, that's a really consistent test.
Yep.
Yeah. So that you can argue with the people that have been arguing against you.
I know. That's what I'm always looking for.
Yeah.
So we are doing a test. The University of Delaware is actually running a destructive test of a decommissioned bridge. Probably going to happen sometime in the fall, where they're actually going to. They have a 2 million pound hydraulic jack.
May I have a suggestion?
Dinner.
We have reservations. My suggestion is we can continue this discussion at the least.
Yep.
And someday during the dinner. But we have 6:30 and it's just about getting that. Okay. Great job.
Yeah.
Yeah.
Yeah, we can go over some. How are we, are you getting solved over there? Yeah, then how did you want to get people over there?
Well, cars. In multiple cars.
I can take a few.
Right, I'm gonna interpret what you wrote here.
So you're gonna go sit on that piece of the right. You're gonna see the hat.
Yeah.
It's like, right.
Raise hands if you're going to the lab and do not have a car.
Yeah. They
Yeah.
don't have
So-
cars to get us over
so
to
between
those peaks.
Brady has a car. And he has a car, maybe has a worker. Right. So we need to have numbers of spaces in cars, so maybe we can raise hands for how much space
And-
we have.
So when's the bus gonna be here tomorrow morning?
Oh, tomorrow morning at 7:45 a.m. You need to all meet in the lobby.
What I will do is I will get in front of my.
This video will be posted online later on, so if you're interested to download it, thank you.
First, to make sure we have all the,
It's in here.